Hello and welcome to today's tutorial. So today we are going to discuss on another application of opamp circuit, that is a differentiator circuit. So let us see what is a differentiator circuit. So differentiator is a circuit in which the output voltage is proportional to the time derivative of input voltage. So now switch back to our screen. So let us see the another definition of a differentiator circuit. A differentiator is a circuit in which the output voltage is directly proportional to rate of change of input voltage with respect to time. So this means that the faster the change to the input voltage, the greater the output voltage change in response. So this we will see with respect to the circuit. So now let us see the circuit here on the screen. So the differentiator circuit is similar to our inverting amplifier circuit. So only difference is that, so let me complete this circuit. I'll use little big here. So if I write an op-amp circuit here, so this is non-inverting terminal, this is inverting terminal, and we will be connecting our input source across this point here to a inverting terminal. So this is our ground point. So this we call it as Vs, and this was our R1 and this is RF. So this is a basic inverting amplifier. So in this case, if we remove this resistor R1 here, and if we connect a capacitor across this point, so this circuit acts as a differentiator circuit. So as we have seen, we know the property of the capacitor, that the capacitor blocks the DC and allows the AC component only. So initially at low frequencies it has a, if you look at here, so at low frequency the reactance of the capacitor is high, so it results in low gain, and then the low output voltage from the op-amp will be generated. And at higher frequency the reactance of the capacitor is much smaller, resulting in higher gain and the output voltage from the differentiator amplifier. It means we'll get a higher output voltage from the differentiator amplifier. So if you look into the waveforms, so if we give these kind of input signals, so what is the output that we will get? That is shown in this graph. So for a square wave we will get a spike output voltages, and for a triangular wave we will get a rectangular wave, and for sinusoidal we will get a cosine wave. So now let us look into the analysis of the circuit. So analysis is quite simple. It carry forward like similar to our integrator circuit. So this is our V0 point, so this is our V2 and this is our V1. So now let us apply Kirchhoff's current law. So let me write the current across this capacitor as IC, and the current across this feedback resistor as IF, and the IB is a current flowing to this V1, that is inverting terminal. So now if I apply the KCL, the Kirchhoff's current law, we know that the incoming current should be equal to the outgoing current at any node. So therefore, so it is equal to, that is IC is equal to IB plus IF. So due to this virtual ground concept here, V2 is connected to ground, so because of which V1 is also connected to ground virtually. Therefore, so V2 is approximately equal to V1, which is approximately equal to 0. In that case, our IB is also equal to approximately equal to 0. So then in this equation the IB is 0. So then we have only IC is equal to IF. So that means we have IC is equal to IF. So the voltage across the capacitor can be defined as C into d by dt with respect to the potential difference across the two terminals, so that is given as Vs minus V1. So if you can see, the potential across the one end is Vs and the potential across the another end is V1, so therefore it is Vs minus V1, and this is equal to If is again the potential difference across this resistor, so that is V1 and V2, so that can be written as V1, sorry, not V2, it is V1 and V0, therefore it is V1 minus V0 by Rf. So we know that V1 is equal to 0, so therefore this equation will become C1 into d by dt, sorry, so it is d by dt into Vs equals minus V0 by Rf minus V0 by Rf. So if we rearrange this equation, so finally we will get this as V0 is equal to minus Rf into C1 into d by dt or into Vs. So this is our final output equation for a differential amplifier, for a differentiator circuit. Okay, so fine, hope you've understood this. So let us take an example here, and before going to an example, I want to highlight here the output voltage V0 is equal to Rf into C1. It means it depends on the time constant and the negative instances, and negative instances means rate of change because it is connected to an inverting terminal, so output will be, it will be in terms of negative. So let us save this page here. So this is page 39. So let me take a new page here. So let us take an example. So here the peak value of the sinusoidal waveform. So let me write here the sinusoidal waveform. The sinusoidal waveform is the input to this differentiator circuit with a voltage of peak value of 10 millivolts, with 10 millivolts, and a frequency of 1.8 kilohertz. 1.8 kilohertz. So we have to find the output, and given that Rf, the feedback resistor, is 100 kilo ohm, and the capacitor C1 or C whatever we can call, so C is equal to 1 microfarad. Okay, 1 microfarad. So now there is no point of writing the circuit because we know how the circuit looks like. So let us quickly jump into the calculation here. So since it is a sinusoidal waveform, we know how to write this. So this is always in terms of Am into sorry, so this is Am into sine of 2 pi ft. So this is a general way of writing any sinusoidal waveform, where Am represents the magnitude of the signal or amplitude of the signal, and F represents the frequency. So this can also be written as sine omega t. Omega, it represents the radians. So now this is equal to, now the peak voltage is 10 volts, so this is 10, it is sine of 2 pi. Now frequency, it is given as 10 kilohertz, sorry, frequency is given as 1.5 kilohertz, so it is 10 to the power of 3. So input is 10 millivolts, right? So rather than writing here, I'll write at the end, so this is equal to 10 millivolts. So now we know the output equation, that is output equation is equal to minus Rf into C1 or C, that is d by dt, differentiate this with respect to Vs. So now we will substitute all the values here and we differentiate this Vs. So I'll leave it to you to substitute and calculate. So finally we know that the differentiation of sine is nothing but the cos, so finally we will get this as minus 3000 pi cos 3000 pi t millivolts. So this is our final output. Okay. So likewise, there is one more example here. So where it is given RF is equal to 1.5 kilo ohms and the capacitor is equal to 0.1 microfarad and the waveform is given. Okay, let us take that example, the second example here. So let me save this page. This is 34, so it will go to 40. So let me take a new page here. So here the input waveform is given to a basic differentiator circuit with RF is equal to 1.5 kilo ohms and the capacitor C1 is given as capacitor C1 is equal to 0.1 microfarad. So we have to draw the output waveform. So the input waveform is given like this. So it's a pure sinusoidal waveform. So it is given. So this is pi. So and this is 2 pi. And the peak voltage here is of say 2 volts. And here the peak voltage is minus 2 volts. So this is our Vs. And the time constant T is equal to 1 milliseconds. So the frequency f we can derive from this time or the time period is equal to 1 by t is equal to its frequency is 1 kilohertz because the frequency is 1 over time, the time period or the fundamental period. So then we will get this. So then the omega is equal to 2 pi f. So we can substitute here and we will get this as 2000 pi radians per second. We will get this as radians per second. Then the final output V naught is equal to 2 sine 2000. Sorry, this is Vs. Let me correct this. So Vs is equal to 2 sine 2000 pi t volts. Now if we substitute this in our equation, that is nothing but V naught is equal to minus RF into C1 into d by dt of Vs. So when we differentiate this sign, we'll get the cosine. So finally we will get this as minus 1.885 cos 2000 pi t volts. I'll request you all to substitute and do the proper calculations. So value might be differ because right now I'm not calculating. So whatever the previous calculated values I have from my workout, so that's what I am discussing right now. So the output waveform is a cosine wave, so either it might be negative or positive. So we'll get like this. So I'll get the output waveform like this. So basically what you have to remember is that you have to remember these basic patterns because in the exam they may ask what is the output waveform looks like. So we can write the equation of V naught, but to derive that output it's not that easy. So it is the cos, it's very clearly understood. Now in this case, whatever the derivation we have done, since it is cos, so either it is if it is plus cos, it starts with the 90-degree phase. Since it is a minus, so we have started with the minus 90-degree phase. That's it. If it is anything else, then we can obtain it. So this is a pi by 2 and so on, it goes like this. And here the maximum peak is, so it is 1.885. so negative peak is minus 1.885. It is minus 1.885 and this is your time t. So y-axis represents the V naught. Okay. So this is one of the examples. So likewise, there are many examples which you'll get it. So we just need to substitute the Vs and we can get the output. Okay, so now we'll move on to the next topic. So next we will going to talk on the source converters. So let me save this page here. Page 41. Okay. So let me take a new page. So let me write here the next title that we're going to talk on. That is a source converters. It means using opamp circuits we can convert the voltage source to current source and current source to voltage source. So we will say this one by one. So first we will going to see the current to voltage converter. So let me expand this. Second, voltage to current converter, and third it is constant voltage source. So let me quickly take this, the first one, the first circuit, that is, first one is the current to voltage converter. So the circuit looks similar to our inverting amplifier. So let me write here, there is only a small change. So this is our non-inverting terminal, this is the inverting terminal. So here there is only difference is that we don't have the input resistance, that is R1, so we can consider that resistance value is 0. So here the current flowing through this point is I1, and this is, we call it as IF, and this is the feedback resistor, as we know, this is RF. So this is our V0. So it is also called as a trans resistance amplifier. So in this circuit, which will convert a voltage to, this is a circuit which converts the current to voltage. So let us see how this will follow. So it's a simple analogy here. We know that the input current is equal to output current here, because the V2 point is grounded and V1 point is virtually grounded due to V1. So due to virtual ground concept, since V2 is grounded, which is approximately equal to V1, which is approximately equal to 0, so therefore we have only the two currents at the node V1, so that is I1 is equal to IF. So if I apply the node voltage analysis at this point, so I have the voltage, that is straight away I1 is coming, since there is no resistor, there is only the I1. And if I talk about IF, it is the potential difference across the resistor RF, so that is VF, V1 minus V0 all divided by RF. So V1 is equal to 0, therefore if I rearrange this equation, so V0 is equal to, it is minus I1 into RF. So as we all know that the I1 current is also equal to IF, so this I can write this as minus IF into RF. Okay. Now if I extend this circuit and if I connect a load resistor at this point, and if I call this as RL, so the current flowing through this point, if I call this as IL, so again the IF is also equal to IL. So then this final equation I can write this as V0 is equal to minus IL into RL. So the output voltage straight away it is depends on the load resistance RL and the current which is flowing through it. So this is a current to voltage converter. So let us quickly talk about the voltage to current converter. So let me save this page here. So this is page 42, and let me take the new page. So second, I am going to discuss on voltage to current converter. So this is also called as transconductance amplifier. It's also called as a transconductance amplifier, and again there are two types, that is VI converter with a floating load and VI converter with a grounded load. So let's take the first one, VI converter with a floating load, that is voltage to current converter with floating load. So the circuit, if you write here, so it's exactly similar to our inverting amplifier circuit. So the non-inverting terminal is connected to ground, and here we will be connecting V sinusoidal wave, that is nothing but an input, that is Vs, and this is R1, and here this feedback resistor is a variable resistor, feedback variable resistor, so V0. So it's a simple, again the same analogy of I1 is equal to IF here, so then we will get the I1 current can be defined as Vs minus V1 by R1, and this will keep it as it is, that is IF. So then the feedback current here, so this again it is equal to the load current if I connect a load resistor here, so this is just, it is Vs by R1. So Vf by R1. So now this is the equation for our voltage to current converter. So let me talk about the second kind of voltage to current converter. Let me quickly save this page here, page 43, and I'll remove this everything here, delete, and now I'm going to talk on the voltage to current converter with grounded load. So with grounded load, so then the circuit looks slightly different here. So it looks like the circuit of non-inverting amplifier. So this is this R1 resistor here, and there is a feedback resistor RF, and this is connected to ground, and we have one more resistor here, we call it as R2, and here there is a resistor here, and there is a one more resistor here, this connected to ground. So this is our load resistor, so let me call this as RL, and this is another resistor R3, and this point is connected here. So here we will be connecting our input source. So this is Vs, this is R2. So call this the current flowing here as I2 because of this resistor R2, and the current flowing here, and let us call this as IL, and this is our V0 point. So this is non-inverting terminal, this is our inverting terminal. So this is a current I3. So let us analyze. So if we analyze this circuit, then we know that the output voltage for an non-inverting amplifier, it is given as V0 is equal to 1 plus RF by R1 into V2, and this V2 is approximately equal to V1 due to virtual ground concept, because V1 is virtually grounded here. Therefore, at this point here, V1 is also equal to V2. So then if I apply voltage divider rule at this point, so then I will get this V1 is equal to R1 into V0 divided by R1 plus RF, which is also equal to V2, because it is approximately, due to virtual ground concept, it's approximately equal to V2. If I substitute that in the current equations, so let me move this entire section to the right side, or let me bring it down here. So now if I write the total current which is entering at this point, so that is equal to I2 is plus I3 at this point. If you talk about, so it is basically the two currents, incoming current, that is I1 and I3, which is equal to the another current, that is IL. So IL is another current which is here across the load. So if we write the load voltage analysis, the potential difference across the R2 can be defined as Vs minus V2 by R2 plus V0 minus V2. I3 is nothing but V0 minus V2 by, or we can write V2 minus V0 also, into R3 equals IL. So then if you rearrange this equation, then we will get Vs by R2 plus 1 plus RF by R1, because from this equation we know that it is V1 is equal to, so voltage divider rule we are applying here, so this is equal to V2 all divided by, this is equal to R3, and this is equal to our IL equation. So then finally, when we rearrange this everything, then finally we will get a final equation, that is IL is equal to Vs by R2. Okay, so this is the final equation that we'll get here for this case. So now we'll quickly look into one more circuit, that is a constant voltage source circuit. So it is same as our, let me save this page here, so save as PNG, so that is page 44 here. So now let me take the new page here. So I'll talk about the last circuit, that is a constant voltage source. So if you want to generate a different voltage source apart from the inputs, then we can use this circuit here. So it's a simple inverting amplifier circuit. So it's inverting amplifier circuit here. So this is R1, so this is Vs which is connected at this point, this is RF, and here the V2 is virtually connected, this is connected to ground, this is non-inverting terminal, this is inverting terminal. So this is the current IF here, this is current I1. So we know that the I1 is equal to IF, and due to virtual ground concept there is no current flowing to V1 terminal, that is V1 terminal is this is V2. So now we know that we will quickly write this equation. So this will leads to V0 is equal to minus RF by R1 into Vs. So this is exactly similar to our inverting amplifier equation. There's nothing much change. It means the same inverting amplifier equation can also be used as a constant voltage source generator. Okay, so thank you for watching this tutorial. We'll join up in the next tutorial, and in the next tutorial we're going to talk on the comparators using opamp. So thank you so much.